Okay, so today we're going to kind of switch topics, it's kind of a hard switch. And the point of this section is to serve as more of an introduction for the 3710 class, right? So what we're going to talk about today is really how microprocessors are built, right? So we've been building digital systems. A microprocessor is a digital system. If you took 2700 from me, you've built a very simple microprocessor, right? If you didn't take it from me, you probably copied and pasted a microprocessor, something like that. So for my 2700 students, this is going to seem very familiar with just the introduction of machine languages, pretty much the very low level instruction formats, right? So 2700, you guys talked about it in terms of opcodes to the ALU, right? That's as gritty as we got. We'll take it one step further. Get the head shakes, those that didn't even get that far. So we'll take it through the opcodes. Don't worry, if you didn't take 2700, this is from me. It's still designed for you. You'll be able to handle it. It's not too complicated. This is just kind of the orientation level stuff. So you've probably heard the term RISC before, R-I-S-C, right? RISC processors. And really, there's this kind of idea of RISC versus CISC, which no one really talks about CISC because we generally, each of these have different processors underneath them. These are like big umbrella categories, and RISC is going to be things that you see in microprocessors like ARM, right? And CISC is going to be see in like processors like Intel's AMDs, and you're going to see them like x86 is one of the example of their architecture, right? Here under RISC, we're going to use a really old one called MIPS, because it turns out it's easier to explain things if they're really old. And then in 3710, you'll talk about kind of newer, updated architectures for how do we use microprocessors. Okay, as with everything, right? The decision of RISC and CISC is trade-offs. So the RIS in this is reduced instruction set, and this is complex instruction set, right? So one of those is, well, they're kind of viewed as opposites-ish, right? Which isn't quite true because reduced is not the opposite of complex, but they are kind of the far ends of the, they oppose each other in a way, right? The trade-offs being around, well, everything that digital power is, right? Speed, power, and complexity, okay? So it turns out that it can be a little bit confusing if you're not careful, because CISC takes fewer lines of code to write, because each instruction can be very complicated. RISC is actually very simple to write and debug, because each instruction does one thing and one thing only. So the whole idea of RISC was in the early days, before they had very complex computer-aided design tools, they were like, yeah, we can build this thing, but if it doesn't work, debugging it's a nightmare. So what they did is they reduced the number of instructions that they could possibly have, optimized it for power, and made it way easier to debug. So the nice thing with RISC is it is one clock cycle per instruction. So a clock cycle happens, it executes that instructions. The result is that in order to do something complicated with RISC, you need multiple lines of code. So the quick example that I use, and we'll dive into it like in kind of the nitty gritty, but is in CISC. Let's say in CISC that we want to multiply two values. So we're going to start off with referencing something called registers, right? So we know what registers are. We use registers to build things like accumulators, store values. We have shift registers. So here we're going to define a register with the $sign. And so if I want my first register, I would say it's register 0. If I want my last register, and we're going to assume 32 registers, which is pretty normal for RISC. Actually, it's about 32 registers. And we'll put it at 31, right? So that's my range of registers. So we're going to use the same notation. This is kind of the RISC, or at least specifically the MIPS notation. It's fairly common that you'll see this notation all over the place, but it is definitely true for MIPS. So in CISC, if I want to multiply, I just write something like mult. There we go. Multiply register 2 and register 5. And notice it doesn't tell it where to put it. It's because there's something called implied operations or implied operands or implied memory in this command, which is specifically that there is some register that the multiplication of 2 and 5 gets stored to by default, right? So other implied memory is like an accumulator. So you could potentially have commands that were like add 5 or like for example, where this again doesn't tell it where to go, but it can have like a dedicated memory register that's functioning as an accumulator that requires a command to unload it into a specific register. Again, implied memory. So RISC as a philosophy doesn't like anything implied. It wants everything spelled out. So to multiply in RISC, if we want to take something, oh, and actually we can take this a step further. So this command, anyway, in CISC, we could also do, and I'm going to just note this. We can also multiply the contents of the memory at n by the contents of the memory at m, okay? Memory is different than the registers. So registers, there are 32 of them in our RISC architecture. The memory is something like RAM or ROM or something that is as big as we want it to be, or at least as big as the number of address bits that we have, right? So if we have 8 address bits, we can have 2 to the 8 memory blocks, right? Instead of the 32. So to do this operation using RISC, so this works in the CISC because it just pulls from memory. To do it in RISC, we have to load mem at n and then tell it where to put it. So we're going to put this in register 7. Then we're going to load the mem at m and put it in register 12, for example. So one operation, load from memory, load from memory. So in a true RISC, like if you were doing pure RISC philosophy, this doesn't work, right? Because again, I don't specify where this goes. However, it turns out in MIPS, they got lazy and they turned this into one of their few exceptions to the rule. And this actually does in MIPS store it somewhere. If you were doing this in a true RISC, then you would need a third register. Something like third, okay, where it's storing, telling it where to store as well, rather than without it makes it implied, right? We don't like implied. The other thing that RISC architectures don't like is flags. And I've talked about flags before, they're going to keep coming around. A flag is something like an extra bit that is asserted if there's an overflow, right? So if I have 32-bit registers and I add A to B and they overflow to 33 bits, which is possible, there might be a flag that says, hey, you overflowed. These flags actually turn it more difficult to start optimizing the architecture, right? So we'll talk about something called pipelining probably next time, where pipelining is pretty easy to explain. But the specific thing to remember here is that flags like overflow, or it's a negative number, instead of using like signed 32 bits, you could use a 33rd bit that's a flag, right? They work, they're fine, they're super common in CISC, but they're avoided because the whole idea, one of the pushes with RISC is pipelining, which is one of the main methods of optimization of a RISC architecture. So I'll delve into the specifics of it, but just so I want to keep saying pipelining, we're not completely lost. Remember that I said RISC takes 1 clock cycle per operation. And if you think back to kind of the ALU, the rough structure of it, right, you have something that, sorry, the microprocessor, we had something called the ALU, right, that is actually doing the math. Well, we're going to divide down that microprocessor, and the microprocessor you guys built in 2700 follows this design philosophy of it has really 4 main steps, okay, where it's going to fetch code. What am I getting, right? So if you wrote 2700, you wrote this fetch command that said, hey, go get the next opcode. Then you're going to decode and ask, well, what is this supposed to do? And decoding can be saying like sending the opcode to the ALU, right? So it went and got it. Now go tell the ALU what it's supposed to be doing, configure whatever selection muxes you need, that kind of thing. Execute is actually doing the math, right? In the case of the ALU, this is just a combinational operation, that kind of thing. And then you're going to clock it in to store the value in some output register, right? And then you're going to have the write back step, which is the storing step, right? Those are really the 4 main steps. This is the RISC steps. We're going to do those one at a time, right? That's the whole idea of RISC, and it's going to take 1 clock cycle per. But the nice thing is, if we design each of these as its own block of logic, we can start fetching one. So we fetch one, we decode it, but decode is a separate operation than fetch. So while the decode is decoding the previously fetched value, fetch can go and get the next one. Okay, that's all pipelining is. So a non-pipeline system has to go fetch, decode, execute, write back, go get the next code. Pipelined is fetch 1, decode 1, fetch 2 at the same time as you decode 1, right? It just has to kind of shove it down the pipeline. The commands are continuous, nothing lays idle. So it's, if this was 4 clock cycles to execute 1 command, it is now 4 times more efficient, right? That's all pipelining is. We'll get into some of the details of what are called pipeline diagrams and some of the more advanced concepts around it later, but I just want you to know. So when I'm talking about flags make pipelining more difficult, that's why. Okay. All right. So I actually don't remember if I got sidetracked before this. One of the main benefits of RISC is it turns out to be very power friendly, okay? Which is why it's used in mobile applications all the time. And then this is not power friendly, but it has more complexity to it. It can do more things. But it takes more power, which is why we use it in like desktop computers, right? We care less about power in non-mobile applications. So specifically the things that make a RISC architecture. I've kind of been mentioning the design philosophy a little bit, but let's specifically spell it out, right? The first thing is all instructions have the same length, okay? So no matter what it is, whether it's an add command, a load memory command, anything like that, it takes, I think in MIPS it's 32 bits no matter what, okay? I actually can't remember if it's 16 or 32. We'll get there in a bit. But it is a fixed instruction length, always the same, okay? This has some pros and cons, right? The pros is it's easy to build a decoder when all of the instructions are the same size. It's easier to program and deal with. However, it becomes inefficient, right? So if there's something, and you can kind of get the idea, right? Just from this load and the memory command. So multiply has to go pull 2 different registers and then store it somewhere, right? So that's dealing with 2 registers. Whereas the load memory is just looking at 1 register. So you can imagine that if this is 32 bits, well, maybe this is 16. Sorry, I guess it has to be more. So if this is an 8-bit address, which I think is true, that's an 8-bit address, that makes 16. And then there's some number for the multiply command of bits, right? Some opcode. So say the opcode is 6 bits in this case. So we have 6 bits here. 8 bits here, 8 bits here. And then what are the rest of them doing, right? So it's a 32-bit command. Well, we'll get into the nitty-gritty of it, but the trade-off that I'm getting at here is that if we have the uniform length, it reduces the complexity of the decode design, but adds a bunch of overhead, a bunch of zeros that we don't really need, right? They're unused. Kind of like in your SPI communication where it's designed, just by protocol that they use, is designed for potentially a 14 or 16-bit ADC, but you have a 12-bit ADC, so there's 2 bits that just don't matter in that I2C stream, right? That's just overhead that does nothing for us. That same kind of things happen here. So it's a little bit less efficient usage of data. The next idea that is, it wants a limited number of instruction formats. So an instruction format is the different ways that we can format a command. So always in the case of MIPS, and this is, I'm going to focus mostly on MIPS, the first 6 bits, as mentioned here, are the command data. Okay. So we have 2 to the 6 different commands that we can use. We're always going to start like this. And then what comes next? Well, in this case, we need just one address, one location, right? And then in this case, I need 2 locations. So for example, if I have one command that needs 1 location, one that needs 2, I'm always going to have location data next. Okay, that's my goal, right? I want to have uniform instructions as much as possible. Turns out MIPS has 3 different formats of commands that it could work with. Whereas something like CISC, some of it like x86, trying to remember, but it has like 18 or something potentially different formats to send the command, right? So it's complicated. We don't like that. RISC is all about simplifying the design. The next is it also wants few addressing modes. Now, addressing modes isn't necessarily obvious what that means, but the idea is how do we go get the address of something that I'm interested in using, like the register address, for example, right? So in MIPS, something like that, we're going to have 1 or 2 different addressing modes, whereas CISC might have 8 or 12 or something. Now, the addressing modes that we'll talk about in CISC include things like direct addressing, which is just give it the exact address that you want. Immediate addressing, which is go get the next one, right? These are 2 obvious ones. This is kind of the ECE 2700 design, right? It has those 2, which is either just go to the next address or go get a specific address and go load that one. But you can complicate it and do like a base plus offset style addressing, which is go get this specific address plus some number, right? So that you can reference, I want address 400 plus 100. So that I take address number 500. That way I could store something in address 500 and know that 100 addresses later, I'm going to get to that result. Okay. There's other like indirect or implied addressing that we have, right? And there's a whole bunch of different addressing modes. RISC wants to keep that as few as possible. In order for RISC to go fast, keep up with CISC, the next design philosophy is use lots of registers, okay? Because it turns out it's faster to access registers than it is memory. So we want to do most of our operations inside of our register values and then limit the number of loads and writes that we have so that we don't slow down, right? And then we want the next step is it wants a load store style architecture, which they just write as load/store, which is what this is all about, is we have to specifically load and specifically store data rather than using the multiply command that I erased that directly pulls from memory, multiplies them and puts it back in memory, right? We have to take the time to specifically do those things. And then the no implied operands, which I've already talked Okay. There's one thing that's kind of buzzed the debate, right? If you went back to the 1980s, there'd be all this argumentation over RISC versus CISC because they started developing better tools. And obviously, there's not one right answer, right? Otherwise, one of these would be gone. However, CISC designers do also like RISC attributes. So they use something that I've skipped over so far that may come back around in this class, which is called microcode, which can use complex operations to turn complex instructions into multiple RISC type instructions. Okay, microcode is basically what the RISC is, where it only does one operation at a time, right? So when we were drawing those state machine charts, chart, diagram, table, chart, right? Where we had some S0 and it would go make a decision and be either true or false, right? The only requirement between being microcode and not microcode is microcode only makes one decision at a time. And then it goes to its next state. There's one decision per state. That's all the requirement of microcode. Whereas if it's not microcode, I can make two decisions. So like X1, for example, could have two inputs. Something like that, right? So these are both checking equalities. So X1 is asking is A or B, and X2 is C and D, and it could decide based on both X1 and X2. Okay, microcode is just make one decision at a time. That's all it means. So CISC can split it out and does frequently into microcode in order to approximate some of the benefits of RISC. But it doesn't get the power benefit, right? It's still power hungry. Okay. What's kind of funny, you'll notice if you go read this book is highly out of date and processors progress very quickly. So if you want to like state of the art, you'd have to go watch YouTube or find a better book or a newer book or something. But it doesn't hurt because most of them have evolved from these early RISC architectures. MIPS is kind of a good representation. So there are a couple different versions. I don't know if I should call it versions. Types of instruction, I guess, is probably a good way to call it. And one of them is arithmetic instructions, right? This is things like add, subtract, and so on. If we want to add, and I'm going to be talking from here on out about the MIPS specifically, not RISC overall. And so in MIPS specifically, if I want to add, this is my add command, where what I'm going to do is I'm going to add the contents of register 3 to the contents of register 4 and store it into register 5, overwriting anything that is currently in register 5. Subtract is the same thing. I would just erase add and write sub instead. There is another form that is common, which is add immediate. Yes.
Sorry, which one would be subtracted?
3 minus 4. And I will double check that really. Yep. Yeah. 3 minus 4. Add immediate or sub immediate. This I means immediate, and instead I would store it into register 5. Add the contents of register 3 to a specific value, 400. That's what immediate says. Immediately add the contents of register 32400. I don't need to make another register call. I just give it a value. Yep. Okay. The multiply example. It's just load. Yep. What this does, right? So if I take an 8-bit number and multiply it by another 8-bit number, I end up with twice as many bits. I end up with a 16-bit answer, right? Because if I add two 8-bit numbers together, I end up with 9 bits. Makes sense that if I multiply 2, I need many more bits than that. Turns out to just double it, right? Just add the two values together. So I would need 16 bits. So clearly, if I'm trying to multiply the contents of a register by contents of another register, I can't store it in a same size register, right? Because if this is 32 bits and that's 32 bits, I end up with needing 64 bits. So what this does, and this is the reason that the MIPS architecture ignored the RISC philosophy in this one case, is because you would have to specify 2 registers to store it in instead. It just adds high and low register, and that's actually what they're called. And high is the bigger bits of this multiplication, and low is the smaller bits of that multiplication. And then you can give it a command specifically to pull the contents out of high or low and store it somewhere. Okay, so that's how this one deals with the multiply command. Is it builds registers that are used for almost nothing other than the results of multiplication. If I wanted to move them out, the command is move from I or move from low. And then I just give it an address of a register. And now I've stored whatever the result, the bigger bits of that multiplication, into register number 12. If I wanted to save that into memory, I would have to go store, which is the ST command. I'm pretty sure I'll come back to that, and then give it a memory address like 4,000. Okay. In MIPS, they do have overflow flags for signed values. Okay. Again, everything just like your SPI and I2C, right? SPI was SPI-like device, I2C was I2C-like device. People design these architectures and then take liberties with them in order to achieve something that would otherwise be difficult. They do have flags for overflow in the case of multiplying or even adding signed numbers. It doesn't keep track of overflow if you add unsigned numbers. So if you were to add a 32-bit number to a 32-bit number and have overflow, it would have no flag to let you know that you did that. So it's kind of on you to make sure that you don't overflow. There is a table on page 433 of your book that takes all of the arithmetic operations and lays them out for you and what they do, which are things like add, subtract, add immediate, add unsigned, subtract unsigned. So add is by default a signed operation as a subtract, which makes sense, right? Then you can do things like move from another coprocessor register, multiply, unsigned, divide, and move from high and low. So if you need to go back, review, you're asked to say, for example, on exam or homework, to write a program that multiplies 2 numbers together given this memory, then you would go load from memory, multiply the 2 addresses, move them from high, move it from low, store it back to memory, right? Which we'll do a more exact example of, but I want you to just be aware of the table 9-1 that has the arithmetic operations. The next type that we have is logical instructions. The logical instructions are things like and, or. You can imagine like XOR, XNOR, and so on and so forth, but it turns out MIPS is RISC. They don't like lots of instructions, so they simplify it down to and, or, and immediate, or immediate. And then they pretty much stop there with the direct logical operations, okay? They don't give you XOR, XNOR. Yes.
Not or inverted?
No, they have no not. What they do have though is well, I'll just write them here. And, or, and I, or I, and then SLL and SL. Sorry. Which is shift left logical, shift right logical, right? Which is just a shift by some number of bits. That's the extent of their logical operations in MIPS. So you have to figure out how to do those things with that set of instructions if you're trying to do a logical operation. Yeah. Okay. Let's see. The next type is memory access instructions, right? We need to get at the memory somehow, since we're explicitly calling it out when we load. As I've already alluded to, this is things like, in MIPS, this is LW, because they use load word is the command, okay? Similarly, they have, it's not capitalized, but I'm going to make it capitalized since it's easier to tell. Store word. In the case of MIPS, a word is 32 bits, unless I'm completely and totally crazy. Yep. You can also store and load half words, okay, which would be 16 bits. You could pick the high or low of 16 bits. So you would do something like load a half word of where this is taking the contents of the memory at S2 plus K. So this is a memory plus an offset, right? And storing it into register 1. So I'm pulling half of the memory and putting it in. You can also do it by the byte. I can take 8 bits, right, of a word. So if there's 32 bits, which there are, a word is 32 bits, but I can take any one byte, any 8 bits of that 32 bits, okay? Which makes this called byte addressable, meaning that that's my access resolution, you could call it, right? It is byte addressable. I can pull any 8 bits. I don't need the whole word, okay? This has kind of a complicated result if you go and just read the book and try to understand it from here, because if each byte is addressable, if each byte has its own address, so let's start at address 0. Do it this way. So if 0 has 8 bits of the word, and I'm going to just use V as my vector, so this is V7 down to 0, right? I'm going to use the VHDL notation, and this is V from 15 down to 8, and so on, right? So what that means is my next address word, my next word address is 4. So if this is V0, I have to wait. Oh, sorry, not this one. This is also V0. This is V1. So it takes me 4 addresses to get to the next word. Okay, so if we think back to 2700, we have this thing called the program counter or process counter, the PC, right? Which keeps track of where we are in our program. Okay, for those that you didn't have me, real quick review. If I want a program to run, right? I'm going to load it into memory and tell it to start going through. It's going to have something like an addressable memory. And each of these memory addresses is going to have a command in it. So like if I want to do this multiplication, for example, in fact, let's do an addition, this addition, right? So in order to add things from memory, okay, I need to first load a word, okay? So I'm going to add two things and I'm going to give it a memory address. So this could be really big, right? Because we have 2 to the number of address bits that we can access. And so we might be at like 128. That's memory address 128. And in order to do that first, I almost forgot, right? I need to tell it where. And in this case, it's number 3. Boom. I have taken whatever is in the contents of the memory at 128 and put it into register 3. I'm now going to take 4, and maybe this is from like 1004 or something, right? Way further down the memory. And I'm going to load that into 4. Then I can add 3 to 4 and store it in 5. Okay, this is what your program memory would look like. And then I would need to store a word, right? If I want to save that result, and I'm going to tell it what register to store it and what register to store, which is going to be 5, and the memory location that I want to save it to. Okay. I may not save it immediately, right? If I'm not going to use like if I don't need register 5 for a while, it's better to just hold it in that register so that I use it instead of storing to memory. The only reason I would store to memory is if I need that value to be held on to, and I need the register that it's stored on for other operations, okay? So we want to hold it in registers because it's faster, right? And the reason in RISC is obvious, right? Because if it's in a register, I can add it. If it's in a memory, I have to load it and then add it. So it adds 1 extra clock cycle. It takes twice as much time to pull it from memory and do the addition than it does just to do the addition. Okay, so again, this is your memory for your program to tell it what to do. This is a program that will add 2 numbers together from memory and put it back into memory. However, the address is complicated because this is just the word index. The actual address is 0, 1, 2, and 3, right? Because it's byte addressable. So I could, if I wrote address number 2, I get the 3rd byte of that memory. Yeah.
So are all MIPS byte addressable?
MIPS is, yes. Yeah, not all RISC are, but not all, but all MIPS is. MIPS is actually like a company specific architecture. I don't think the company exists anymore. But you might have, which is super rare, you might have like a bit addressable, right? But then you need 1 address for every bit, which is a huge waste of resources because your address needs to be much longer to care about the same data, right? Which is the same reason you might not want to be byte addressable. You might want to be word addressable, right? And if you go buy RAM or something, even flash memory, a lot of times they'll specify, right? And it kind of works up bit addressable, byte addressable, word addressable, page addressable. And we're not going to get into pages in this case of memory, but pages is just some number of words that fit into a convenient number of words in what they call a page. And so a lot of times you can read out a whole page really easily. Okay. Anyways, you don't really need to know the page level. We're not really going to talk about it, but that's the next step up. So we are byte addressable. We're kind of in the middle there, and we can pull 8 bytes. We can also store at the word or byte level. Okay. Anyways, so this point, the reason I bring this up is so that when I get to the PC, the processor program counter, when I step to the next line, right, the PC is what keeps track of where I am in the program. It remembers what I've done essentially, right? It doesn't increment by, we would think +1, right? Because we're going to go from 0 to 1. But we're byte addressable, so it's actually PC +4, so that I go from 0 to index 4. So when it says, if you go look at your book, use this example and see that it is PC +4, that's why. Okay. The book does a poor job of explaining that, so if you read it, just be aware. It explains that it happens, explains that this +4 is necessary, doesn't really explain why. Okay. The next type that we need to talk about is control transfer. Now, this is just a fancy way of saying that we need to be able to compare things, right? Because right now we can do just about everything else. We can do logical operations and or we can add, subtract, multiply, divide, shift left, shift right, but we can't if, right? Which means right now, without any other thing, we can't do even like a for loop. So that's what this is doing, is giving us the ability to write in for loops or if statements, conditionals, which the first one we'll talk about, the easiest one to talk about, is branch if equal. Okay, that's all that's saying is we're going to compare two registers and ask if they're equal or not. Okay, so I've been doing this way. Actually, I'll point this out. So I forgot that I shorthanded this when I wrote my notes. So I forgot. This MIPS architecture uses actually an S before the address when we're doing a register. So like I write 5, but it's really S5. Sorry, I forgot the S. Doesn't really matter. Not a huge deal. It's just representation. So what this is going to do is it's going to ask really the question is if S1 and S2 are equal, go to this address. So PC +4, that is just next command, right? Go get the next command. That's all the PC +4 is. And then the K times 4 is that I'm going to go ahead K number of commands. But in order to get the number of commands, I have to multiply by 4 because each command takes 4 addresses. Make sense? Okay. You also have branch if not equal, BNE. You can set on less than. Okay, yeah.
Those are kind of like the jump command if you're the microprocessor.
Almost, but jump is just, so we'll get to jumps. That's actually a command that it has here. So the difference is this is jumping if.
Jump 0, jump not 0.
Yeah,
Oh,
so it also has that, which I'll do the comparison when I start explaining these specific jumps, right? But branch and jump are closely related, right? It's just a conditional jump is really what you describe it as. Okay. Set on less than SLT or set on less than immediate, okay? And all that these are doing is it's going to do a comparison and then set a register to a value. So for example, I could ask the question, is register 1 less than register 2? If it is, we then would write, well, I'll just do it this way. This is probably, okay. Basically is if 2 is less than 3, then contents of the register 1 would get set to 1, otherwise 0, right? That's what set is, right? Set is go to 1, otherwise reset, go to 0. Set on less than immediate, instead of comparing two registers, can compare a register to an immediate value. Okay, that's all I really need to say on those control transfers, but they're just ways of doing this comparison, enabling us to do loops and comparisons. Okay. There is one minor limitation, is that because there is a limit of 16 bits for K, because that's just how many bits they've allocated inside of their fixed command length, right? This is one of those problems that comes up. One of the trade-offs to RISC being simple is that it wants to follow the same thing. So it can't, for example, use extra bits for K when the command is fairly simple. It has to use 16 always. So your jumps that result from this comparison are strictly limited to plus or minus. It can go either way. 32K. I can't jump further than that in my memory address. Okay. Right, and this is actually one of those things that we can simplify, is we set less than, we don't need a greater than, right? Because you can just flip the order of them and you're done. Right, so that's one of the simplifications that you have, is no shift greater than. Jump, right? Now we're going to talk jump. The commands for these ones are J for jump. If I wanted to jump some number, I would just jump, give it an address, whatever that would, and it would jump my address to there. This is JR is jump registers, okay? Which is going to go to a specific register number. So it's going to set your process counter, PC, right? The thing that is keeping track of where we are, to the contents of this register. Right this way. So this is not set it to like 32, it's set it to the contents of whatever is in S1. Okay, that's what this jump register is doing. The next one is JAL, which is jump and link. This is very similar to the other jump commands. All it does is it turns out in the MIPS architecture, I said that there were 32 registers, right? The last one, register 31, right? Because we're zero index, so it's n-1. The 32nd register, or register number 31, is used for linking. And all that does is it keeps track of where we jumped from. Okay, so jump and link, it says jump somewhere and remember where I was, so that then I can go back there easily, right? This is, again, kind of an exception to the typical RISC because this is an implied address. Nothing stops me from writing to register 32 without this command. I can just write there as 31, as it would be called, right? But I can use this, which is an applied memory address. So again, another kind of exemption from the typical philosophy. Okay, so let's do the kind of example that you might be asked on. Where you're going to say, let's see, the example is write MIPS assembly language for the following program that adds two arrays, X and Y, each of which has 100 elements. So basically what we want to do is we want to change kind of this abstract programming to MIPS, which is so 1,100 times, we're going to take the contents that's Y at I, right, where I is counting, and we're going to count up. Then we want to add them together and store it in that location. So we're just adding the index of X to whatever's at Y. Okay, so counting up by X. It also says assume that X starts at the address, the memory address 4,000, and Y starts at the memory address 8,000, right? Okay, so they're stored in memory. We need to go ahead and use these commands to make a for loop. So the first thing that we need to do is, well, this depends on your architecture, but what they're going to do is they want to make sure that there's nothing in current registers. They're going to restep registers. So they're going to, actually, let me start higher than this so I make sure I don't run out of room. Okay, what this is doing is AND immediate, register 3 with 0. If I AND something with 0, it sets it to 0, right? And then I put it back in register 3. I have now cleared all contents of register 3. I'm going to AND immediate. Right, quotes means just copy the same line above. So I'm going to do this to save myself some writing. So AND immediate 2, 2, and 0. Clear register 2. Oh, I understand what I read wrong. Whatever pseudo program they're looking at, or maybe this is a language that I just suck at. It's 1 to 100, not 1,100. Okay. So that's why this 400 is there, is it's the number of addresses multiplied by 4. Okay. Now I need to start getting things out of memory, which I've said where they are, right? So we can now do LW which is going to go ahead and take address 4,000, 4,000, and stick it within the register 15. Nothing's in register 3. We know nothing's in register 3, right? This is an offset, so we're offsetting with nothing. LW 14. Again, take 8,000 with no offset. That's all that is saying. And now we just want to start adding, right? So add the values. Oh, that's 14, I would hope. Contents of 14 and 15 and go throw it in register number 24. SW is store whatever I just put into 24 into 8,000, which is Y, right? That's this part. Take the thing that I just stored, which is X plus Y, store it in Y. Because Y and X are memory, okay? Not registers, they're memory. So that's why we need the store word. Once I've stored the word, let's increment, right? We're going to take whatever's in 3, which is the first time is nothing, and add 4. This is keeping track of our PC, right? So our 3 is going to be basically our PC address. So we're jumping from 0 to 4, or you could look at it as we're jumping from 4,000 to 4,004 to go take the next value of X and add it to the next value of Y. And then I forgot that they did this. So they go back, and this label is I can go mark a register, and I'm going to do that back here at my first load, right? Because that's what I'm going to go back and do. And so they add this command label : which says I have labeled this row to mean my branch if not equal location. So if 3 and 2 are not equal, then we're going to go ahead and branch, okay? So 2 is 400, okay? So what's 100 times 4? We're going to do that 100 times. And if we're branch if not equal, so we're 4, or yes, we're 4, right? 4 is not equal to 200, therefore go to label. If it is equal, right, the other condition, then we do whatever's next. Program marches on. Any questions at this point? Okay, so this is still not bit level operations, right? This is still representative of register 3, for example, which is not bits, which is ultimately what a computer cares about, right? That's what we understand from VHDL and the digital design, is this is still not the lowest level programming language we can get to. So what we want to do is talk about the different formats of commands that we can take, which is where we're going to start looking at the actual bits of like the add command, right? So there's 3 formats that it can take. R type, I type, J type. J type is jump commands. I type is immediate commands. And R is everything else. Okay, so adds that aren't add immediate fall under R. If it is an add I, it falls under the I type. Now, what the different types mean in this case, all right, the different command types are what is the expected format of the bits, okay? So all right, so 20 plus 12, 32, it's a total of 32 bits, broken down into sections about that big. Where the first one is opcode. And it turns out the same, right? We're always looking at opcode. Now, they do this really stupid thing that I absolutely hate in MIPS, where in the R type, this opcode is actually always 0, no matter what the instruction is, because they actually use the last 6 bits, because it turns out they need 6 bits to have enough commands as their function. So the 0 opcode just says, hey, go look at whatever is in function. Okay. This is what we mean by the disadvantage of unifying the length of a command, right? That's what the first bullet point under the what is RISC philosophy is unified command length. That's the downside. We have 5 bits of 0 that just don't matter in an R type instruction. Okay. So the first one, which is another, most of the time is a waste, shift. It uses those 5 bits to tell it how far to shift. Okay. It only cares about this guy if it's a shift command stored in the function. Otherwise, those are completely and totally wasted. Then I want to make sure I don't mess up these ones, right? Because these ones, it's obvious kind of what it's going to be, which is, so this is telling it to add, subtract, blah, blah, blah. These are telling it, the 3 of those are where from, which requires 2 different registers, and where to save it. Yep. So this is where from, this is where to. Okay. Source, these are both source, destination, that's why B. Our destination, which looks like read, which is stupid, but okay. The I format. The I format is immediate. So if I want to add the contents of a register to a value, for example, right, that's one of the immediates. Add I is an immediate command. It just looks something like, well, I need a source register. And then it's going to actually take advantage of the next little bit. Oh, sorry, RS. And use this as the offset or the immediate value, right? So the I instruction is now also used for any of the memory commands that require an offset. It is also used for add I. The J command, jump, is again opcode, and then it's just going to break down all of these barriers and look at it as address. Okay. Those are the only 3 different formats that they use. Now you could imagine if they wanted to be clever, if they needed more usage, they could have more command structures, and then they could use the bits in different ways, but they followed the RISC philosophy here where they want to have a few different versions of command structures, which again simplifies the logic that you have to design, because when you go look at these, it's a very limited number of decisions it has to make when it goes and tell, right, the controller is going to look at this and go send out a bunch of commands to the data path to tell it how to behave, right? This is that controller data path concept that is true for all digital systems. The controller is going to look at this, send out a bunch of commands. That command decision structure is fairly simple when there's only 3 different ways to start structuring the commands. There is on page 440, I'm not going to go through it, how it breaks down the actual bit encoding for each of these commands. So for example, and there's also a table 9-8 that if you want to, this is a mess. I don't have time to go through it. I was planning on it, but I don't have time. Where it on 440, it gives you an example it wants to build machine code equivalent to the following assembly language, right? So when I write these kinds of things, this is the assembly. When it references machine code, that's the 0s and 1s, right? Because that's what the actual machine cares about, where the 0s and 1s. And so it gives you this big long table of what each of those commands actually are. So for example, the add function has the bits 31 to 26 are all 0, right? As I said, because it's not at immediate. The bits 25 to 21, so the next 2 down, in this case, they're going to have 2 bits there. And anyways, I'm not going to go through the thing, but it gives you basically how to build this table. So this table is an instruction for and immediate 3-3, and it says that and immediate, if I wanted to do this, is well, and immediate is different, right? Because it's an I code. Because it's an immediate, and it wants to do that is the opcode for and immediate. Okay, and then it wants to and immediate with 0, right? We're clearing that register. So what we want to do is take the register. So let me write out this real quick. It wants to take the contents of register 2, and it with 0, put it back in 2, right? That's how we clear a register. That's what the goal is going to be. So we need to take register 2, 5 bits. I now have register 2. I wanted to go into register 2. And then I want to do it with 0. So it's just 0. Right? That's the machine code, or the ones and zeros, that represents the assembly language. You're never going to write in machine code, right? This is like encoding that's behind the scene. If you're trying to write very efficient programs, you may write in assembly. You may end up someday getting stuck writing something in assembly. If you take 3710, which is kind of the follow-on to this course, where it's still digital systems, but you're transitioning from VHDL and FPGAs to microprocessors and embedded systems, okay? So the embedded systems, I'm pretty sure Dr. Brown is the only one that's likely to be teaching that in the near future, and he does make you write in assembly. We have one person that's taking it that can attest to that joy.
Next semester.
Yeah, it's a great class, right? And a huge number of jobs in the area require either VHDL and or embedded systems, right? These are very common very common jobs in the area. So we're trying to solve problems using FPGAs and embedded microprocessors, right? Because that's just how the future is going, right? You're not going to be building simple logic gates anymore. The breakdown tends to be if you want to do something that is heavy signal processing that requires complex operations like convolution or multiplication, it is faster in FPGAs, right? Because FPGAs are fully parallel. Whereas embedded systems are going to be sequential. They're going to have, right, this order of load something, multiply it, and so on and so forth. It has this kind of queue. So, but it turns out that embedded systems are good at their own things. And sometimes like simple operations, like maybe multiplication. If you have a multiplier on board, you can still do it in one clock cycle. If you don't have a dedicated multiplier, there's no way that it's really going to pull that off, right? Multiplication is actually kind of sophisticated as far as digital logic goes. Have you guys started building that multiplier? Now that I've talked about it, I have the assignment due. I don't remember when, but oh, is it today? How are you guys doing on that multiplier?
Almost sad.
I'm almost ready.
Okay, so if I give you like 2 more days, you won't waste it.
No, I wouldn't. waste
Okay,
it.
okay. So I heard you guys don't have Gibbons homework, so I can make you suffer with this.
No, yes.
Anyways, that's my stuff for the day. All of this can be found in the book. You can go back and reference. You're going to need some tables when this assignment comes out. It's not super exciting, but it is one of the requirements that we have to have for this class is to introduce you to this. And then next time I'll start talking about pipelining, which is ways, how do we start optimizing some of these architectures. All right, dismissed.
No.